Second, so as speaker, I believe you're entitled to take off your mask. Technically, I think we all
okay.
definitely.
Even better.
Yes. And yes, so welcome everybody. We are back in person once more at the CUNY Logic Workshop with Alexei Miasnikov from the Stevens Institute. As I recall, it was rich algebraic structures, was it not?
Okay.
And weak second order logic.
Right. Okay. Again, thank you very much for coming and waiting. And I'm really sorry about this. I will try to make up, so I will just do every even slide. So, I don't know. But I'm in a hurry. My jokes are getting much worse, so you should. What is? Yeah. That's my question. How expressive is first order logic in groups? And I will try to explain that sometimes it's unexpectedly very expressive. So there are several ways, and people tried all of them to measure how sort of this first order logic. I will talk about groups, but whatever I say actually applies to every arbitrary structures in finite language. So can you describe a structure up to isomorphism and say that for group theories, but for logicians, and say cardinality, something like categoricity, or it's another way, you can say it's good logic because in this structure A, you can describe by these sentences or formulas a lot of objects associated with it, subgroups, whatever, many. Recently it was proposed, maybe not very recent, but already about 20 years ago, maybe this is less. So structure, let's A be finitely generated. A is first order digit if for any other finitely generated B. Elementary equivalence implies isomorphism. So it's a big restriction that the other one's not just countable, but finitely generated. And it's quasi-finitely axiomatizable if there is one sentence related to A, such that any other finitely generated structure B, it satisfies this statement if and only if it's isomorphic. So you don't need first order theory of A, just one sentence, much stronger. That was with respect to the first approach, up to isomorphism, what you can say. Second one is related to so-called Maltz's problem, and he stated it for free groups, but in general, people now refer to it as describe definable subgroups in a given group. So you're given a group, what subgroups are definable by first order formulas?
You always mean that you're only allowed to use the language of group theory?
Yes.
Or, okay.
Yeah, just language of group theory. You have multiplication, inversion, and constant one if you need. So pure, nothing, very poor language. So his take was, he described what are finitely generated three nilpotent groups elementary equivalent to each other. What does it mean? And he proved that they are isomorphic. And the idea was the commutant is definable by a formula. So the quotient is interpretable. So if you have two free nilpotent groups, you take quotients, they must be elementary equivalent. Finite three abelian groups finitely generated, it's all known for a long time, they're isomorphic. So that implies that the ranks are isomorphic, and since they're free, they're isomorphic. Similar idea here. Here, commutant, it's subgroup generated by commutators. And it's known, it's a verbal subgroup, in other words, generated by values of one word. It's called finite width. So every long product of commutators is equal to some fixed number of factors, if you take. Here it's different thing. Three solvable groups, commutant is not of finite width, but you can do the same thing. Commutant is definable. It's more complicated, but so three solvable groups of finite ranks are elementary equivalent if and only if they're isomorphic. That's what Maltz proved. And then classical matrix groups, he was thinking about if you have GLN over a field and another GLM over another field, elementary equivalent, what does it mean? And it means that if ranks are more than 2, ranks must be equal and fields are elementary equivalent. And he used definable subgroups a lot in this statement. So that's actually a good question. So he stated it for 3 groups. And it requires solution of taxi problem for 3 groups. To prove, we did it with all then later by Perrin, Pillay, Linus, and Ten, that if you have a 3 group non-abelian, it means non-cyclic. So it's just few subgroups are definable. It's cyclic subgroups. And definable, it's allowed to use constants here. So cyclic, it means you take an element A and consider all elements which commute with this very simple formula, centralize it, and it's cyclic. And nothing else. Of course, all subgroup, because it's cyclic group, you can write down. But the whole group, of course, and the identity subgroups, and nothing else. So the commutant is not definable. And ranks are not, the rank is not definable, and bases are not definable. So it's very, very poor from algebraic viewpoint. What you can do, you can say something about equations and topology. So that's a different story. The same was true for torsion 3 hyperbolic groups. So for Molus group, it's true. It's kind of, but those who are close to figures. So if you take abelian groups, only finite digit subgroups are definable. It's very easy to see from elimination of quantifiers for abelian groups. So for nilpotent, it's much more interesting, but I don't want to say a few words about it. So the question is, let's go to opposite to 3 groups. 3 groups are too much, it's too hard. I don't like it. But what are groups where all subgroups are definable? Finite groups, of course. Infinite cyclic groups, yes. If you have subgroup generated by element 5, all elements belonging to this element, it's y, so x, which is equal to y plus y plus y plus y 5 times for some y. So it's very simple formula. What else? I start thinking it's not clear, really. So let's have to the extreme that you can hopefully can say, yeah, not many groups. So subgroups in G are uniformly definable if for any n there exists a formula in n variables plus 1, y, besides that for any couple of elements A1, A, and B, Pn holds in G on these elements if B belongs to the subgroup generated by these elements. So it defines uniformly all n-generated subgroups. So, and that was my question. I thought, yeah, of course. So, except for maybe something really strange. The question was, are there infinite groups with uniformly definable subgroups? Finite are uniformly definable because it's finite.
Are you making any assumption about the existence of subgroups? I mean, there are pretty nasty symbol groups and stuff out.
Yeah, but I'm not talking about normal subgroups, about arbitrary subgroups.
Okay.
Absolutely arbitrary subgroups.
Groups with no non-trivial subgroups at all?
No, that's only cyclic of order prime P.
Okay.
Nothing else. Otherwise, you have always an element that generates a subgroup.
Yeah, okay, right. Sorry.
So not 3, not often 3, not Z, because subgroup generated by element 5 and subgroup generated by element 7, they have different formulas. It's not proof, but it shows. And if you start thinking, yeah, again, you can go to elimination of quantifiers and do something. Not find this rated abelian. So are there any such groups actually? It turns out a lot. Famous Baumstadt-Soliter groups, 1N, meta-abelian groups with a relation. It appears everywhere. So groups generated by 2 elements, and relation is just these products of cyclic of ODN and Z, free meta-abelian of finite rank, the famous Thompson group, SLM, so reasonable rings, algebraic or Q, finite algebraic extension of Q. Non-uniform higher rank arithmetic group, that's complicated object, but a lot of them. Chevalier groups. Then algebraically closed groups. There are much more examples, turns out. So some of these examples are mentioned in our paper with Olga and Mahmoud Safrabi. It's Gakta book number 2. So about rich groups. It's a nice book about group theory and model theory. Pillay, one of the authors, Sklinas, Haas. It's based on some complicated results by these people. I'll say a few words after it. But it's strange. A lot of groups. And
is it easy to, there are a lot of groups there that I don't really know. Is it easy to say what an algebraically closed group is?
yes. So take algebraically closed field and then think about groups.
Think about groups.
So it's essentially closed. Think about the model theory, it's easier. And it is essentially closed model. In groups, it will be the same as algebraically closed.
And does it wind up being strongly minimal or something like that? Or...
No.
No. So is it obvious that it's on that?
Yeah, it's we are set algebraically closed fields, but not in this respect. It just you do the same structure. You add roots,
Okay.
and I will say a few words about it.
Okay.
About the algebraically closed groups.
Okay.
But then it turns out if you took some properties like that, strange properties, for example, if subgroup is free. As I said, there is no formula which or finite or infinitely many sentences in group theory which says that group is free. It's a lot of elementary equivalent groups to free groups finitely generated, which are not. They're complicated. When it's finitely presented, is it residually finite? We have every element there is a homomorphism from this subgroup onto finite group that the image is not 1. Or the conjugacy problem is decidable, say, in polynomial time. You start sort of thinking about this, and then for some of these groups, you prove it. And then it's when you prove that, yeah, what you prove what? That for every such property, there is a formula again in n variables such that it's true on element, false on elements A1 and if and only if the subgroup generated by these elements satisfy this property.
If the conjugacy problem for that subgroup is decidable in polynomial time,
Yeah.
that's
Yeah.
the formula for that?
Yes, that's kind of.
Is it only for if it's in polynomial type, not just if it's decidable in general, or is it both?
You can replace polynomial time by any measure which is arithmetic. That's a hint. But when you start looking at this, it's not group theory clearly. There is something else there. So must be something going on. And then I was trying to solve the multi problems for some groups. But then it turns out there is this phenomenon. And the question is, first order logic, it seems like quite powerful. How to measure? From my viewpoint, the best way is to how to measure how great is it the expressive power, where does it come from? Because it's not quite clear why these groups they have these properties. And that's what I would like to answer. So we are talking about logic. So I thought that first order logic is expressive but some more powerful logic. That would be a reasonable answer. Like L omega 1 omega. I knew it's not true, but something like that. But then the first question, which I didn't think much, it's for logicians, actually. Other infinite groups where the first order logic is as expressive as L omega 1 omega. Again, I want to go to the extreme to say, obviously there are no such infinite groups. And we are happy. But when I think a little bit, not really quite clear. So the upper bound is this logic or second order, which I didn't believe, still do not believe, but that would be the limit. First order is as equivalent as expressive as the second order.
So can I just ask what do you mean by having the same expressive power?
Yeah, I will say few words, not few words, I will explain right after this slide question. Right now, intuitively, you can express by first order formulas as you can express by second order. Mm-hmm. Say, so you have variables running over elements, you have variables running over sets, subsets, predicates going on. So it turns out the correct answer is a big second order logic, and I will get into it quickly. So we'll say that algebraic structure is rich if the first order logic over A has the same expressive power as the big second order logic over A. And I need to answer your question here now. First. There are, I don't know, you know better than I do about weak second order logic. From algebraic viewpoint, from my viewpoint, this is one good way to describe what it is. You need to define the superstructure HF of A, or smallest admissible set. As usual, you start with the set A, and then you take A and all its finite subsets and iterate. You got a set, and then union with all finite subsets of this. So these are sort of elements, and then you build up all finite sets from this and take the union. They're just a set. And then when you have, suppose A is a group for simplicity, A is a group, you have to just multiplication. So now I would like to make it into a structure. A has basic set of elements, this normal A. You take two sorted structure, one sorted, I'm sorry. All these hereditary finite subsets, sets, you have a predicate which defines A in here. So you don't need two sorts, it's just one sort, kind of trick. You have multiplication defined on, sorry, they don't type multiplication, but defined on A, the elements defined by this predicate, and there is membership predicate. So basically, it's all kind of set theory on finite sets over it that basically you can do, and you can so it's a superstructure over it, but it's first order. We have it enriched language, but it's first order. You can define similarly for arbitrary structure. So from the viewpoint of, say, cryptoplastic or something, it's this first order theory of this much more powerful structure is the same as weak second order theory over it. Suppose it's the definition of weak second order logic. It's not. Sometimes people, I will say few words. So what you can have? You have variables over elements in A. You have variables running over sets. You can write down the formulas as usual using the language of this structure. So you have all these formulas. And now it's a definition. Structure is rich if for every first order formula phi in the language of bigger structure, HF of A, there is a first order formula phi star in the same variable, three variables x1, xn, in the language of A now, much poorer, just group C. Such that for any assignment of variables where element belongs to A, to the group, HF of A satisfies this formula, powerful formula on this element if and only if the original structure A, without any, satisfy this formula on the same elements. So here you have quantifiers over sets, blah, 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 blah. Here is just, say, pure first order. That's what it means rich. Another way how people put it, it's an arithmetic fragment of L1 omega, omega 1 omega. What does it mean? We start with first order language L, and we can see the fragment on this powerful logic. For you, I can explain probably much easier than the group series. You have some standard enumeration of first order formulas. And now you apply infinite conjunctions and disjunctions, and you build up and you enumerate. So enumerate all these formulas effectively. So in this fragment, you're not allowed to use arbitrary infinite disjunctions, conjunctions, not arbitrary, restricted. So which ones? So you have a set of formulas that you already built in your fragment. I would like to explain the inductive steps, how to take which conjunctions, say, or disjunctions are allowed. So first of all, the set of indices should be arithmetic. So it's sort of effective set of formulas, not arbitrary, it's arithmetic. Then they have uniformly bounded complexity. So what is complexity? As usual, alternation of quantifiers changes complexity +1. And I'll say a few words, just a second, get to it. All variables should be free variables in this list. So it's when we take infinite conjunction or disjunction, it will be in these variables. And complexity increases. So index, the pi n index of this set, arithmetic set, should be taken into account. So it's all formulas here, the complexity is bounded, say, by R, and S is the pi n index of the arithmetic set of indices. Then you can take infinite disjunction. So basically you have arithmetic set of formulas, that's precisely what it means. You can take disjunction if all these formulas in three variables x1, xn, complexity, all of them is bounded, and then you take it, and the complexity will be maximum of this thing plus 1. Anyway, should I say a little bit more or not? When I give a talk to group theories, they say, "Oh, now we'll discuss," and you're very sorry. So,
I have a question.
Yeah. Good.
Do you kind of go into like omega 1 CK, or do you go up into omega 1 when you're talking about
Omega 1.
Okay.
Omega 1.
But you did say arithmetic.
Yes. Right. Arithmetic for sure. Conjunctions. Logic. Omega 1. But arithmetic, it's just sets in arithmetic hierarchy. It means in arithmetic it's definable. I'm sorry. Yeah, I didn't get it. What you're asking. So it's definable in arithmetic, in standard arithmetic.
Yeah, I think this is what some of us would call sigma infinite or sigma omega computable. Something like that. Maybe not computable.
Yeah, if you start with sigma 1, it's computably enumerable,
Yeah.
and going up
Yeah.
during Turing jumps. Another way to look at it. So, long time ago, Belayev and Tyson, two logicians from Novosibirsk, they proved that this logic, the fragment and HF of A are equivalent. What does it mean? You take this logic, which contains infinite disjunctions and finitely many variables. For this formula, there exists a formula 5 star in the same three variables in the language of superstructure, which defines the same tuple cell of elements in A. Right? So A sits in both. Here is just A. Just formula is complicated. And the converse is also true. So in both, so they're equivalent.
So that's what you mean by having the same expressive power, essentially, right?
Yeah.
But there is a
Yes. Right.
Is it effective?
In that proof, not, but I will say about it. It's good. You participate in all my slides already. Now just illustration. So suppose we have a speech group. So first order logic is equivalent to the second weak second order. It means it's equivalent to this arithmetic fragment of L omega 1 omega. So why all subgroups are uniformly defined? Fix M, consider variables x1, xn, and then effectively enumerate all group words. It means inverses are also there. By 0, 1, and so on, effective enumeration of all words. The set of these formulas, of course, it's arithmetic because it's computably enumerable. So you can take disjunction. What the disjunction says, y is equal to the value. It's a product, some product of these elements, and all products are enumerated here. So what are group words? It's just products of this longer products. Element y belongs to the subgroup generated by x1, xn, if it's one of these products of generators. So that's a conjunction. Since it's rich, this conjunction is equivalent to some first order formula. It's not quite easy to do what the formula is. Now, maybe group theory, but much more simple object. It's a free monoid or free semigroup with identity. So it turns out this monoid is rich as well. You pick finitely many elements, you generate a submonoid. There is no cancellation, nothing, it's just all products. And there is very simple formula in using just multiplication, nothing else. which describes all these things, the submonoid. That's kind of strange, but if you know that you can use this type of formulas, of course it's easy. Okay, so how, yeah. My point was examples, all these groups are rich, actually. So first of all, the logic of this, all these groups is equivalent to the weak second total logic, whatever incarnation you take, HF or arithmetic fragment, doesn't matter. It's based usually on some deep results about these groups. But for example, here it's a McIntyre, Trofimov, and I will explain. Here it's based on Kiliv, that would be Lipezolga, Prolompovich. Thompson group is kind of Kiliv, this is Mahmoud Sahrabi, things. This is Lubotsky, Arvi, this is Seagal and Ten. But this is just a few of them. Three monoids or a lot of unrelated monoids turns out to be rich again. So it's very, very powerful. First of the logic there. ZQ. Because C is obvious, sort of, if you're in recursion theory, what you have all n tuples you can enumerate. Anyway, that's sort of. So how one can get richness? So for this, it's by interpretability of structures. That's the tool, at least I used. I don't know. I assume that you're familiar with when one structure is interpreted to another. So by interpretability is each of them is interpreting the other. That's the first condition, mutually interpret, but not enough. And the second is you take B interpreting A. Interpretation, it's some set of definable set of tuples, quotient set modulo definable equivalence relation, formulas define predicates and everything. So it's a structure is amorphic to B star. It sits inside A somehow on the tuples. And then it's isomorphic to B, but A is interpretable in B, so you can interpret in here. By transitivity, A star is interpreted over here. So it's bi-interpreted if there is a formula for A which defines an isomorphism from here to here. So what is it? These are classes equivalences of some tuples. Here it's take these classes, make longer tuples and another equivalence relation, but you can bring everything back to A because you say, yeah, you take representative of this class, you can say something and it will be true for all. So you can define an isomorphism by formula. And the same for B. So it's bi-interpretable. It turns out it's much more powerful. Here, one can use constants, which is sometimes not good for interpretability, and then it's very interesting. But let's just stop. Oops, what did I do? Yeah. Picture. I don't have time for the picture. That's famous sort of Heisenberg group. 3 nilpotent of class 2 and on 2 generators. Matrices, upper unit triangular matrix, so easy. It's it's mutually interpretable with Z, but it's not bi-interpretable. It's classic kind of example. Interpretability is due to Malthus, but it's interesting that if you take finitely generated nilpotent group, every such group is mutually interpretable with Z, and you can prove a lot of things. but none of them bi-interpretable with Z, and that's discouraging. You look at abelian groups, nothing bi-interpretable with them, really interesting. Look at nilpotent groups, almost there, but not.
Z itself. Z itself is not.
No, Z is interpretable in G, set G.
No. But is Z itself not a possible G finitely generated? With no
Yeah, but Z, it will be, in this case, it will be just addition, no multiplication, because it's a group.
Okay, wait, but it's not interpretable in itself.
Z, yes, with itself, but it's a ring, it's not an important group. That's what I'm saying.
You thinking of Z as a ring here?
No, I'm confusing everyone. And that's how we do in group theory. Try to pretend that the results are harder than they are.
Okay.
So here it's integers with addition and multiplication.
Okay.
Before I use Z, which is tradition, it's a cyclic group, just addition. Okay, sorry.
Okay.
So the main theorem is like that. If A is bi-interpretable with HF of itself, then A is rich. And that's, if you think, it's not difficult, because here you can express everything which is weak second total logic over A, but it's bi-interpretable. So you can translate them to formulas. It's not quite clear why you need bi-interpretable, and you need it. So it's not obvious, but you can feel something. If H of A is interpretable in A, every formula somehow, it might be, the problem is that HF might be interpretable in A on very small piece. About this piece, you can use infinite disjunctions, but outside, you don't know. So you need bi-interpretability. So a little bit more harder, if A is bi-interpretable with HF of anything, then it's again rich. Or A is bi-interpretable with the rich structures, and A is rich. And as I said, N, Z, or Q are rich for recursion sort of serious standard tricks. I will say a few words later. We prove that finite abelian groups are bi-interpretable with Z, since they are rich. That's very, very non-trivial thing, because it answers a lot of questions about them. For example, it was a question: is there a formula which defines all bases of these groups? You can't do it in three groups, but in abelian you can. It's QFA, it's prime, and it's homogeneous. Homogeneous means if two tuples realize the same types, they're conjugated by an automorphism. So it's very, very nice. It's strange. It's not nice from one viewpoint. For example, it's no way it's stable, because Z interpretable there. So it's bad, it's not stable here. But on the other hand, it's so bad, it's as bad as arithmetic. And arithmetic is really good, because you have a lot of things to work with. So it's not stable, but it has a lot of rich things within its language that you can use all the arithmetic. That's a nice theorem, recent. Every infinite finitely generated integral domain is bi-interpretable with Z. So from the result I already showed, it is rich. So in rings, there are a lot of rich rings, actually. Every integral finitely generated integral domain, that's a lot. So all of them are extremely powerful first order language in these structures, in these rings. And Diekman and Pope, again, it's a lot of non-trivial number theory. Basically, forget about characteristics, say 2, infinite finitely generated field. say, number field. It's rich. By Julia Robinson, Q rationals is definable. There, it's famous result by Julia. But it turns out it's bi-interpretable with Z. This is the first result, which says richness is not about it by interpretability with Z. It's much more. For example, if you have three non-abelian groups and K is an infinite field, and we will take K of F, which is a group algebra. So it's formal sums of elements from the group times coefficients with linear combinations. And you multiply and add up as usual. It's a kind of important whole object in algebra. So it turns out this algebra is bi-interpretable with HF of the coefficients, which is strange. So it's not about the group, it's about coefficients actually, but it's HF. For example, K could be uncountable. So it cannot be, this group is uncountable, cannot be interpretable with Z because Z is countable. So there is no Z in this picture at all, but it's rich. And there are a lot of such examples. For example, free associative algebras, not commutative. Free associative algebras, the same thing. As a ring, you don't need even algebra action, just a ring. It's bi-interpretable with HF of the coefficient, so it is rich. To prove this, we used least superstructure. If you think about sigma definability in admissible set theory, they use these structures because it seems like HF of A, it's not constructive, it's for mathematicians, sort of. But least, so what you need? A is a structure. You add arithmetic as a second sort. You take the third sort, all lists over A, and you have concatenation, that's not notation for concatenation, the length of the list. So it's a function from here to N, and T, you have a list, and I's component, let's say A is I's component of S.
So that's a relation.
Yeah, that's a relation. Yes, it's not, yes, it's a relation. So that's a list superstructure, it's called. You have anything given right there, and list. It turns out it's yeah, I didn't see. Is it here? How come? So it turns out this thing is bi-interpretable with HF of A.
The same.
Yeah, so it's the same power. It just very naturally appears in the three associative algebras, group algebras, three other algebras like that. So it's very natural to have that. Types didn't prove it, but they outlined this logic, arithmetic fragment. And if you take all these great algebraists, they studied existentially closed group, rings, semigroups in some classes. For example, the following classes of groups or torsion free groups or semigroups with cancellation, inverse semigroups, many. They have existentially closed objects. And every time, if you look at the proofs of these guys, it turns out what they proved, but there are key ingredient that you can show that all of them are rich. So it's always there is some lemma which says that this structure, another structure, is interpretable in the existentially closed object. What is this? You have your structure, you have the second sort, which consists of all finite binary predicates. And you have a relation such that XY pair belongs to the predicate P from here. It is just membership to the, so it's very sort of poor structure. It turns out it's by interpretable with HF of A.
Cardinality goes up, right?
Yeah.
Yeah.
Yeah. Yes. Right. Well, otherwise, it's okay. Yes, you're right. So there is a key lemma which says these predicates are interpretable in the algebraically closed things uniformly. There is a term which sort of does it. Complicated though, but it's known that if you have non-trivial algebraically closed group, it's also existentially closed. So it's the same object. And algebraically closed groups were studied a lot. So in other words, every non-trivial algebraically closed group is rich. In particular, every countable group embeds into a countable algebraically closed simple group. So it's embeddable into a rich group. So it turns out there are a lot of rich groups in terms of countable ones. Take IBT group or semi-group, which is from the class I described. It's always embeds into algebraically closed object, which is rich. Turns out it's much more than that. If you look at countably infinite groups, I should shut up. They form a Polish space with a suitable metric. And standard notion is a group property P is called generic. If the subset of groups in this Polish space satisfying this property is big, or called Kamiga. Okay. So recently this team show that a generic infinite countable group is algebraically closed. So most of them countable groups are actually rich. So yeah, that's so what take all infinite groups. There is a metric, standard metric on it, which makes it Polish space. And there is a notion of Kamiga sets, which it means it's not measure one, but something large set. So typical terminology is, so it turns out they prove that algebraically closeness is a Kamiga property. So most of the group countable groups satisfy this property, so they're algebraically closed. That's what it means. So it's actually, if you most of countable groups turns out to be rich, which is strange. I have to finish. So
You can go another 10, 15, 20 minutes if you want.
oh,
So, yeah.
and beer comes with it? No. Sorry. Not, oh, I shouldn't be joking. So there is a record, right? I don't know. Maybe it's not working. Okay. So Kelly and Mies prove that if the structure is by interpretable with this, then it's quasi-finitely axiomatizable. So there is one formula, one sentence actually of the language of the structure, which characterizes all finitely generated structures elementary equivalent to the given one. Just all elementary equivalent finitely generated ones should satisfy this statement, and that's it. All of them. But what actually is going on? That's a general statement. If you have a rich structure in finite signature language, if A is generated by a finite set with an arithmetic diagram, sort of multiplication table is arithmetic. Okay, again, you take the enumeration, and it's arithmetic set definable in arithmetic. Then it's QFA. It was missed here because whatever is bi-interpretable with Z is arithmetic by definition, because to interpret you use formulas in Z, so it's arithmetic. But you don't need to interpret with, for example, the three associative algebras and other algebras I showed. They are not bi-interpretable with Z, but if coefficients are good, arithmetic structures, then those algebras will be arithmetic, they are rich, so they will be QFA. So, for example, take three associative algebra, non-abelian. Abelian polynomials also true. So there is one sentence which holds in this algebra such that all other finitely generated rings satisfying this sentence will be elementary, will be isomorphic to it. So it's kind of strange to me. It's prime and homogeneous. So strange because Z is prime and by interpret always prime is prime. So it's a very interesting question related to, maybe you know the answer. Finitely generated group is arithmetic multiplication table. Is it true that only arithmetic types can be realized in this group? Or think about semigroups if you think it's easier. So it's multiplication table is arithmetic. It's given by arithmetic function. Take a tuple, all formulas which satisfied by this tuple. Is it arithmetic set of infinite set of formulas? But
Do you know the answer to that question? Or
no. It's some question for logicians, I think. There is very interesting problem we discussed with some algebras. So Boris Plotkin, he was developing so-called logical algebraic geometry. So algebraic geometry, the classical ones, you have solutions of equations, polynomial equations, say, in complex numbers, so real numbers, real algebraic geometry, classical ones. But why not to take formulas instead of equations? Kind of natural, right? But when you think, complex numbers, first of all, there is elimination of 25, so you don't need 25. Then it's integral domain, so you don't know core. Because AB is equal to 0, A is equal to 0, or B is equal to 0. Then you don't need negation, because X is not equal to Y. It means X minus Y is not 0. It means it's invertible. So there is an element that you multiply is equal to 1. So you don't need negation. You still have an equivalence relation when you take interpretation. Think about it. You have a definable subset modulo some equivalence relation. And then Bruno Plaza proved that it's there is a elimination of imaginaries. It means you don't need this because there is another definable set which is the same thing without equivalence relation. So what classical algebraic geometrists did, indeed, it's enough to have equations or the same thing for reals, elimination of 25s, elimination of imaginaries. So the whole thing. But over arbitrary structure, it's nice to have formulas. So Boris Plotkin was developing this logical geometry. That's very natural question. So what's the question?
Sorry, what was this? When did you do all of this?
This logical algebraic geometry.
No, like when did he do? When was he doing that?
When?
Yeah.
Late 90s he started. It's a separate, very interesting, from model theory, it's extremely interesting stuff, if you think about it. He went to unfortunate direction, because you have, no, I'm not saying why it's, so you have in classical algebraic geometry, you have algebraic set, and the corresponding algebraic object is the coordinate algebra, right? Coordinate algebra. And since it's algebraic objects, which has much more properties, you can study coordinate algebras and go back to algebraic set. That's the whole point. Here, if it's not real or complex numbers, the corresponding algebraic object is Tarski algebra or Hallmark algebra. I don't know. Nobody looks at it now. So it's very particular. The same Galois theorem as for relations between algebraic sets and coordinate algebras here as well. But the objects are they're not groups, they're not algebras. Not much is known. You go there and you can get any results and go back. But if you look at different things, there are very interesting things. That's very interesting general model theory question. You have two finitely generated groups which realize the same types. It's called isotypic. Is it true that they're isomorphic or not? Standard techniques like, I don't know. Like Arithmetic Types, it's not working here. So what you would like to maybe some, I don't know. That should not be true from my viewpoint, because it would be very good, strangely general, but not clear. What is this? You thought a little bit if you can do something like forcing here, or you need to construct something strange, but it's finitely generated.
Why does it look at me?
I don't know. Okay, sorry. Now I will look at someone else. The last thing I would like to say. So if you go to what's called handbook on logic, there are handbook, and look at what is weak second order logic. Sometimes it's like that, sometimes it's like that. And now I understand that all this equivalent, now we can prove that they're all equivalent, including these incarnations of weak second order, they're convenient in applying different algebraic structures. Sometimes this one is good in algebra, this one is good algebraically closed objects, this one is good. And it would be, if you start sort of using them in groups, or this one is perfect, as we discussed. But it would be nice to have, yeah, by the way, this is equivalent to this one. Instead of arbitrary arithmetic, it's enough to have just recursive.
They're the same language?
Yeah, the same power. Less formulas here, but it's the same expressive power. So when you're working with a rich object, you would like to use all of them simultaneously. It's convenient. For example, to say that subgroup has polynomial time decidable word problem, you would like to have this because you would like to define a subgroup, as I said. And then you need to have natural numbers to say that number of steps is bounded by a polynomial. So you would like to have this and that simultaneously. And what we proved is Vladimir Belyaev last year. So all these incarnations are equivalent, but critically, it's effectively equivalent. So given one, that's what your question really. So it's supposed to be punched. But you already. Okay. That's why I'm looking at you.
I didn't know the answer. Really.
Yeah.
I made it even more punchy, I think.
Yes. It's not easy. You need this system of notations and standard kind of, was standard maybe some years ago, not standard for algebraic. But they're equivalent effectively, and there is a universal sort of universal weak second order logic which contains all of them. As I said, it would be nice to use them simultaneously. So there is add whatever I mentioned in one logic, all this kind of big stack of all things. That's your new logic. So it's equivalent to each one of the incarnations. And then if you have each structure, then for every formula of this logic, you can effectively construct equivalent formula in the first order language. We know that every formula, because it's rich from this structure, from this language, is equivalent to some, but not quite clear how to find it effectively, but that you can do all these things. And it's so now you can use lists, you can use sets, you can use predicates, you can use whatever in this logic to describe it. So if you have each, for example, group, it's very difficult to find something which is not describable by first order logic, because it should not be in the arithmetic hierarchy somehow. So you need specialists to find something which is not definable, or take a reasonable ring, which 100 years ago reasonable would be probably maybe integral domain or something. It's rich, so it's very difficult to find something which is not first definable. So yeah, that's the last slide. Thank you very much.
Okay, so questions? Something in mind if nobody wants to go first. You?
All right. So you said that for any given structure, the translation procedure is effective. How much does it depend on the structure? So I would imagine it's must be always kind of a class of structures for which it's the same translation process, or like, is there something like?
No, it's in a sense, yes, the language should be finite, of course, say, but then you by interpret, say, HF of A with A. By interpretation involves some formulas which defines by interpretation. So if you take by interpretation to other, say, elementary equivalent structure, it will be absolutely the same formula, the same procedure. So, but if the interpretation uses different formulas, so first order formulas will be different. So it depends on the by interpretation. But it's a good question, because you can, and I thought that Roman would be here, so for him, you can.
Roman, want to speak up? Muted right now.
Oh, okay.
Oh, no, I'm here. Oh, I'm here.
Oh, hi, Roman.
Hello.
So you have a say group which is interpretable in Z. Most of groups like solvable problem means it's interpretable in Z, hyperbolic. Now it's interpretable by some set of formulas. So think now about in terms of logical geometry. In the classical case, we know what is algebraic group. It's algebraic group defined by set of equations, algebraic sets, right? Graph of multiplication is algebraic set and so on. Now think, let's take all arbitrary formulas. So general algebraic group scheme is a set of formulas which interpret this group in some other structure, for example, Z. Okay, now take non-standard arithmetic and use the same interpretation, the same algebraic scheme. So it will be a group. It turns out it has extremely close properties to what the original group was. So it will be hyperbolic, but it will be acting not on Z space, but not Z tilde, say, non-standard space. It will be a lot of properties. So it's very interesting objects. For example, you can determine what are non-standard polynomials. And it's similar to non-standard reals, because what are non-standard reals? It's a field which is elementary equivalent to reals. If the group is interpretable in Z, there will be some other elementary equivalent groups which are not like that. But if it's bi-interpretable, then all elementary equivalent will be non-standard models using this general algebraic scheme. So that's a way to kind of solve kind of the old approach, to Tarski problem. Tarski said, given a structure, find all structures elementary equivalent to given one, which is impossible in most cases. Because what is this? So for finely generated, it's much more, but it turns out they are just non-standard models, and they have very good properties if you look at the by interpretation. So I don't know, Roman, that's what I wanted to talk to you afterwards. Maybe we can zoom.
Well, I think this is fascinating. There's certainly much to talk about, but well, first of all, one should talk to McIntyre about all of that. I think you know it already starts with those ZP, the rings, this non-standard P. And it's already somewhat complicated, but I think it opens the door to what kind of things to think about, right? Let's start.
Yeah, that's probably, okay, good. Thank you. So you will tell me more about this, I hope. Okay, sorry. We should be engaging people outside.
Yes, it's good. It's good. I'm keeping an eye to see if any of them raise hands already. And this is allowed, folks, if you're online. Yeah, okay. Erin?
Okay. Oh, thank you for the talk. And I'm sorry, a lot of it kind of went over my head. But could you say what I saw meta-abelian? Can you say what meta-abelian? What a meta-abelian group is?
Meta-abelian, yeah, it's you take the so-called derived subgroup or commutant subgroup generated by all commutators.
So let me share the slides. I can see you right on the board.
Yeah. So formally speaking, solvable. See, meta-abelian is solvable of class 2. Sorry. So go to Galois theory, so solvable groups. But class 2 is meta-abelian. It means there is a normal subgroup A, which is abelian, like that. And the quotient is also abelian.
Okay.
So it's a class 2. I'm sorry. I should be saying it's a solvable class 2.
The owl is having trouble here because you write, but then when you're writing, it is projected there. And so the owl moves over here and it gets projected again. And then the owl is in logical deep trouble. Anyway,
So if you do Galois theory, you take Galois group responding to just one extension like that.
Okay, thank you. I mean,
I'm going to ask, I'm assuming all through here, when you said interpretation, you were using just plain first order formula.
Yes.
Yeah. There are ways of extending that notion, right? I mean, this is something that Antonio Montalban, I think Harrison Trainer and I worked on, Alexei Miasnikov, you know,
Yes,
other
yes.
people too. Would they be useful here at all? You know, effective, you know, computable sigma one formula?
Yeah, I think it will be, yeah, of course it will be useful because if it's effective, you can translate still formulas from one structure into another one in efficient way to equivalent formulas. That's right.
Because I mean, there are theorems here, I can't point to one right now, but where I was thinking, okay, you know, by interpretability here gives you something. What if it's by interpretability via, you know, effective sigma one formula, sort of computable pi 5 formula?
Yeah, that's. I think you can go up. Good question.
I mean, in some sense, what you're trying to do is to get away from those things, right? You're trying to say, okay, you know, everything that you can express in HF of A, you can express right back in A. So, you know, you don't need all of that. But
on the other hand, it still will,
tool.
Yeah, it still will be very good because if it's by interpretable, say it's rich. So consider the sigma n pi n hierarchy using formulas not on arithmetic but over the structure.
Mm-hmm.
It's still proper hierarchy actually. It's and even if you use Blum, Smale, Shoup machines, it will be jumps there.
Mm-hmm. Mm-hmm.
So it's a reasonable thing. If you start with, say, formulas for interpretation, which is already in sigma 5, you are missing this part, the initial segment, but
Mm-hmm.
still, it's you can say all other formulas are kind of equivalent to these ones in the original group. So yeah, that's that.
That connected up with ways of taking a structure from one class and producing a structure in another class where, you know, where isomorphism is respected and things like this. And even with a sort of functorial way where you can take an isomorphism between structures in one class and map it to an isomorphism over here. And I don't quite, but if there were it may be obvious, I'm not seeing it yet, that if you could do this sort of in both directions so that you had the identity functor by composing, that would make it obvious.
Yeah, I think it's
both rich or neither rich or something like that.
If it's again by interpretable in this sense, then you have really both ways and you have equivalence in the corresponding say category.
Mm-hmm.
It's which is very good. And yeah, it will be just not first order, some harder formulas, but yeah, I would think it's very similar. Yeah, I just don't know the examples probably in groups where it's interpretable as Z using sigma 5 or something. Would be good to look here.
I had a question on one of those open problems you mentioned. It said, what did it say? It said something about arithmetic types.
Yeah.
What exactly do you mean by arithmetic types? Like types of arithmetic formulas or types that are themselves?
No, yeah, the set of formulas is arithmetic. It means you take the standard enumeration of all formulas. You have a subset of formulas, take the corresponding subset of its numbers, and it's arithmetic, definable in arithmetic. Yeah.
So all the possible formulas in the language.
Right.
Okay.
And you take But type those formulas which are realized by some tuple of elements, of course,
Right.
in this structure. So it's related to the structure. It's not just related to the theory.
Right.
So that's why it seems like it could be true.
Okay.
Do you know any structures that are not rich?
Yes.
Any natural?
Yeah. So I believe nilpotent finely generated are not rich. It's not easy to prove, but it's true.
Okay.
And free groups are not rich because rich groups they have uniformly definable subgroups. In free groups, hyperbolic groups from the theorems I showed only cyclic ones, so they're not very close to each one. It's but some groups which supposed to be the examples I choose here, it's from different types of groups. Arithmetic, matrix, Chevalier, it's sort of similar, but then goes to Thompson groups, F and B as well. I didn't mention that it's both. They are rich, and you go to metabelian, there are a lot of metabelian groups, rich. So, yeah, it's kind of strange picture. So from not clear what was rich, but now it's many famous groups are rich. That's a bit strange to me. Okay, so last 5 questions.
Yeah, sure. So, like you said, amongst the countable groups, we have that generically they are rich, and then you also said that, right? So I think that Z was an example, and then B by interpretable Z would make you rich. And so, like, are there other like natural, I guess, like by interpretability classes that you get amongst the countable groups, like besides for just Z, like other like representatives of by interpretability classes?
Yeah. It's sort of cheating, but you say SLN over a ring, say special linear groups. Ring should be, say, commutative. You don't want to go to what is determinant in non-commutative case. You can do some, but say commutative ring with identity. So it's SLN R over ring R. If n is more than 2, it's by interpretable with R. So this type of things for Chevalier groups, or yeah, it's a lot of algebraic groups like that. I didn't say anything, but many of them. Classical matrix groups, of course, are this type of examples, but algebraic groups are natural class. But what is interesting, you go very far from algebraic, like free metabelian, suddenly it's rich, or free monoids, sort of just words. That's for me kind of really strange, because it's so poor, you can't express anything. But by Queen's theorem, you can interpret Z, and this interpretation that he did long time ago, it's actually by interpretation if you look. So it's rich. And then suddenly you can do whatever you want in this monoid. And since in the quotients, other monoids, you can do a lot. And groups is difficult because there is cancellation. In monoids, it's you can do things.
You use the word poor very often, and it's not the opposite of rich.
No, it's funny because when you're talking about first of the theory of free group,
right?
And algebraists would say, so tell me what you can define by these formulas, and it's complicated. Then it turns out it's not algebraic objects, but it's topology. It's a GeoG decomposition of some things. There are a lot of surfaces you can define. There are a lot of things you can interpret there. You really can interpret. but it's not groups. So no groups. Cleaners show that even infinite fields cannot be defined. So it's the first example of stable theory where fields are not infinite fields, not there. I don't know. So it's poor in this sense. But then if you go to this technology, suddenly you have, so it's rich. Now it's interesting to me, and I think, so in algebra, always finitely generated objects were good. In model theory, quite often it's because Levingame's column theorems, I believe it's countable and so on. So countable are not good because you can emit types, you can construct a lot of kind of things, elementary equivalent, but strings. So, but if you go to higher dimensions, it's sometimes getting better. But now it's clear, so finitely generated case, it's absolutely unstable because sometimes, but it's very good. It's really good. It's like you're doing number theory. It's so rich. It's interesting. It's a lot of things. And compare, for example, to abelian groups, which are quite often stable. But what can you do there? That's why I'm saying it's a little bit poor. So.
May I have your attention, please? May I have your attention? This is your fire safety director. We are conducting a test of the fire alarm system. Please disregard any tones or alarms. This is your fire safety director. We are conducting a test of the fire alarm system. Please disregard any tones or alarms.
I think I'm going to go ahead and stop the recording now.